See if we can get everybody started up here. So it looks like we have a pretty intimate class today. I'm not sure where everybody is, but we'll see how it goes. Maybe that might inspire more conversation than we've had. So there doesn't have to be straight lecture all the time, but we'll see. So today we're going to talk, well, before we go into, we're going to talk about constraint-based scheduling, but before that, just a couple of announcements. First of all, the 421, the second NLP, Natural Language Processing lecture, we're going to have a guest lecturer, Professor Eric Nyberg of LTI, and he's going to be talking about the Q&A, questioning and answering technology that was in Watson. So I'm sure all of you have heard of Watson, and I think that this will be actually a great lecture. So I think we're pretty fortunate to have this. Also, Zico's not going to be here today in class, but he will be holding his normal office hours from 3 to 4. Okay? Okay, great. So today we're going to talk about constraint-based reasoning, but constraint-based scheduling. But before I'm going to go into talking about that kind of scheduling, I'm going to go into some more basic questions, and you can't get much more basic when it comes to scheduling than to say, what is scheduling? So we'll talk a little bit about what scheduling is, and we'll try to, if you guys think about a little bit about scheduling, you know, it's like ordering steps to do resources, to do things. Should sound really familiar, similar to something like we've had prior in class, say planning. So we're going to try to distinguish a little bit between where scheduling and planning is. That distinction used to be very hard and fast. It's gotten a lot more murky in between now since then. All right. We're going to go into some the basic constraint-based scheduling models, sort of ways to solve the problems. We're going to something that's a little bit different. Almost all the stuff that we've talked about, except for the end part of our planning, we've just talked about solving static problems. Here's a problem, you know, do an identification of this. Here's a problem, generate a schedule. Here's a problem, you know, here's the answer to this thing. What we're not talking about now is this continuation of a problem over time as things change. How do you keep adapting and resolving that problem? Because in real life, as we know, most of the things that we do are processes. They're not static events. We have processes in our lives. And so things change over those processes, and we've got to constantly adapt and accommodate those processes. And that's going to be talking about how do we measure manage that scheduling change. We'll go into more distinction about planning and scheduling and where there are synergies between planning and scheduling. And finally, then we're going to go and talk about something that's coordinated distributed scheduling agents. And the reason I really want to bring this up is I don't know how many, I've gone to a number of thesis defense, and I don't want you guys to repeat this error, where somebody will ask them, they'll present a centralized approach to doing scheduling, planning, coordination, and then they'll say, oh, you got to be kidding me. Huh. I'd like to know why this happens to me every time. I'm sure it's something about me, and if you can identify that, I'd appreciate that. Sweet. Okay. All right, I pray and hope that this won't happen again. All right, so as I was saying, often when you see these thesis defenses, you'll see somebody they'll get a question inevitably. It'll be like, huh, that seems organically to be a distributed problem. And your approach is centralized. You have some centralized reasoner making a decision. And they'll say, oh, well, it's a straightforward transformation from centralized to a distributed problem solving. It's not straightforward. It's never straightforward. All right? Don't answer that way. So you have to be aware of that, and we'll go into some of the details about why. In this case, we're going to be talking about scheduling, but we'll talk about why distributed just really changes the ballgame. All right? And finally, only if we have time, we'll go through this coordinators, a distributed scheduling case study. And what's great about this example here, if we get to it, I hope we do, is that all the things that we talk about here, you'll see in here. It had every aspect of it. And so it's kind of a fun example to look at in a sort of a grounded way. Okay? okay, grounded application. So the first thing is, what is scheduling? All right. So the first thing that we'll notice about scheduling is assume that we know that there is some set of activities, an operation, another operation, another operation, and that you have some process plan enumerated for you. It's elaborated for you. You already know what you have. What you don't have is an assignment of resources to that process plan in order to accomplish those. All right? So scheduling for right now is going to be a way of ordering those these operations such that they obey the constraints that are given in the problem, and also can have to obey by any kind of ordering that you have to put in based on your resource assignments. All right? And so what we're not doing here in this particular case is we're not deciding what activities to do. Remember, in planning, we were deciding what activities to do to accomplish some goal. Here, we know what activities we have to do, and now we have to assign some resources to it and order those operations in order to accommodate both their hard constraints and also the resource constraints. So in this example, we have op1, op1, we have a job up here with 3 operations. We have another job down here with some other operations. We have a release date, and we have a due date. And by release date means that this cannot start any earlier than this time, and due date means it shouldn't finish any later than that time. All right? Same thing with down here. And then we have these resource constraints. In this particular example, these are precedent constraints. And precedent constraints are defined here as saying essentially this one can't start until this one is started and its duration is done. So it's the start plus the duration. This has to equal to that or greater. Okay, that's simply what a precedent constraint is. And these are resource ordering constraints. And they basically say that this may be, the order of these may be done because they're done by the same resource here. So you can imagine they can either be done this way or this way, right? Depending on which way you want to do that. So that's essentially what this says here, is that either one operation has to come first or the other operation comes first, but they can't be done at the same time because they're being serialized by the usage of the single resource here. All right? And then finally here, all this is doing is a definition that's saying for this release date, all the operations have to start at that time or later than the release date. All right? And then in this example, again, here is an example of an objective function. You may have multiple different objective functions depending on what you want from your schedule. This is the simple one that says minimize the difference between the deadline and the completion times of the job. All right? And given some formulation of a scheduling problem like this, some kind of problem input, you're going to find a solution. And the solution is assigning these operations such that you're going to minimize this and that you're going to assign the resources to accomplish those tasks. So you'd have something like this, something very simple. If you think of these as resources and you think of these as the timeline of the resources, how they're going to be used, this is the schedule where R1 is doing op1 and 2, and R2 is going to do op1 1 and op1 3, and notice that this is starting before this and this is finishing before this starts, and that observes these constraints here. All right? So again, we're having a distinction between this and planning in that we already have the task that we're going to have to do here. We're not making decisions about it. Later on, you'll find out we're going to do some scheduling where we actually do make a decision about what tasks to do, and then it gets a little bit murkier between scheduling and planning. Okay. So just briefly, we'll go again here, just to reiterate what I was saying, is that planning is a synthesis of action sequences to achieve goals. We've all seen this a number of times, right? And here we have this other idea, is just we're doing the assignment of the resources. And by assigning the resources, we're also imposing constraints on the ordering on both timelines here. All right. So in recent years, it used to be that this was the major distinction. These guys decide what to do, what sequence of tasks to do. This assigns what resources to do it and when to do it. All right? But, so we have all these kind of planning from this aspect. We don't really, planning would plan almost irrespective of resources. Wouldn't think a lot about resources. Just think about what steps it had to do. And as you moved out, scheduling would then assign the resources. But as you start thinking about more resource constrained planning problems, planning has to think about resources because the choice of what step to take next is very much constrained by what resources are available. So planning is starting to push that way. Scheduling, on the other hand, is that when it starts to have to think about, oh, if I'm going to go do that thing, there may be a whole set of setup activities that I have to do in order to do that. And that may be, depending on which resource I'm doing it on, suppose I was on a machine, and the machine was configured in a particular way, and I had a job I was doing on that job thing. I have a new job I have to then do, and I say, oh, that machine is configured perfectly for my new job. Then I don't have to do anything. But if I did it on another resource, I might have to do a completely different setup, and I might have to organize and plan some steps to set that machine up in order that it could handle this new job. So now planning here, scheduling here, has to then figure out steps that it has to do in order to accommodate the new job on its timeline. So here we have pushing this way, we have scheduling actually making decisions about what tasks to do. Also, it shows up a little bit later, and we'll talk about it when we talk about utility maximizing scheduling too, which again has to decide which ones to do in order to maximize that utility. Okay, so a little bit more. Scheduling is fundamentally concerned with coordinating multiple process agents, efficient use of shared resources. It's totally focused on resources. Processes known in advance, action selection, pre-specified alternatives, restricted notion of state, availability, usage of shared resources, again, allocating those resources in order to accomplish those pre-specified states, and the determination of when and how, but not which steps. Okay, that's usually planning. All right, so there are lots of ways to do planning, and what's going to be interesting is that we're going to touch on lots of techniques that we've already seen, just cast in order to do the scheduling problem. But before going into that, into the constraint-based scheduling methods, I want to talk a little bit about some of the other methods that are popular, and they should all seem really familiar to you because you've all seen these methods. All right, at least parts of them. So one of them is optimization, is determination of tractable problem classes, mathematical programming models, right? Mixed integer problems. So again, these things, these are all methods that you've seen, and you're probably thinking, when do I use one or the other? One of the problems up to fairly recent, and still contains, is that the naturalness of making a natural problem into a mathematical sort of a topology that makes it work for the mathematical methods. They don't always work very well. You'll see that criticism a lot about it, and that's why you often don't see it. Also, there are corner cases which often are not solvable in the mathematical ones, and that causes issues also. So again, it criticizes idealized and otherwise restricted problem formulations. This is changing, but there are still many cases in which you still have this criticism is valid. And then the other one on the extreme ways is priority dispatch rules. And the idea of priority dispatch rules is that you make these very local, greedy decisions. All right, here's my next thing I got to do. All right, that one's longer, that one's longer. That's the shortest one. I'm going to do shortest one first. I'm going to do that one first. Okay, that's my job. And so you make these kind of very quick decisions. It's actually very good strategy in terms of when you have high uncertainty in the environment. Because no matter how much you do predictive scheduling out in advance, if you have high uncertainty, then you're not going to be able to, every commitment you make is unlikely to be a very good one. So these priority rules work very well. Also, if you have to share lots of information, then if you're unable to share lots of information, dispatch rules work pretty well too. So from sort of the AI perspective, I think of the symbolic representation of time. When you think of scheduling, you have the symbolic representation of time, and we'll talk about what that symbolic representation looks like a little bit, different ways to look at that. Resource capacity constraints. You often are going to formulate these constraint-based model methods as search. So this will all be very familiar to you. The emphasis is on a broader picture, and as I said earlier, we're not going to just solve the static problem here. We're going to solve this ongoing continuous process versus the static optimization problem. Something over time as the problem changes, okay? Larger problem solving context, the integration within planning. How does planning and scheduling work synergistically? Is there a good way to do that? And then you're operating in this dynamic and uncertain environment. All right, so all these are great AI themes as you've seen so far in the course, and scheduling is just another way, it's a domain in which you can reflect and see how those problems bear out and manifest themselves. All right, so over the last 15 years, I'd say the major advances in the techniques in solving practical problems are these constraint solving frameworks. In fact, you use some of them. The incremental mathematical programming models have gotten much better, as I said. And the meta-heuristic search procedures, ways of looking across different parts of the search space, not to get caught in those ravines and those plateaus that we talked about earlier, have all improved. They have portfolio methods and lots of different methods that we'll mention. And several significant success stories, which is a big deal. Planning, unfortunately, doesn't have a lot of these things to point to, but scheduling does. But it's not surprising, because scheduling in some ways is a more limited and structured problem. You know, it's not making these wired decision problems. And commercial enterprises and tools. All right, so let's go to the basics of constraint-based scheduling models. Sort of the very, very highest level is that you have these set of ways of allocating the resources to the tasks that are part of the problem that comes in. You have heuristics for searching those, some of which will work faster and shorter. You're pruning the search space. You maintain a current solution, and you have a constraint propagation engine, some engine that will propagate the temporal and resource and capacity constraints such that you're always guaranteed to have a valid solution. So this is sort of like, think of this thing as kind of this way of always propagating the values around. We'll show you a little bit more detail about that. But basically, it's ensuring the consistency of the solution. All right? And this will ensure the consistency of the solution and maintain that consistency as this makes decisions. As things arise, resources fail, new tasks arrive to the network, you may have conflicts that you have to react to off the existing plan. And you may have to retract from that plan and add new pieces to it. And we'll show examples of that. But as that happens, you're going to come back, and often you may do iterative construction methods on this, or you may actually come back and reconstruct the plan depending on which way you want to do that. All along, depending on this constraint propagation, to ensure consistent solutions. All right? It's very, it's general in the sense that you can almost put any kind of problem, a scheduling problem in it, and it's very easy because the constraints make it so that it's kind of composable. And when I show you some of the constraints in the propagation engine, at least in terms of the temporal constraints, they're generic enough that it's independent of the domain. So it makes it nice and general to do that. The incrementality of keeping this steady state solution and then trying to correct that solution has some benefits, in particular when human beings are involved in executing schedules. You have problems with cognitive dissonance when you have, if the schedule, imagine if you were doing something and every step you took, suddenly the plan changed on you, right? You know, you go like here, and I was going to go to UC, but now it's telling me to go to Wien, you know, and you didn't know that. So that cognitive dissonance is a problem. So that kind of stability in the schedule helps a lot. Incrementality also helps in the computation of the schedule. If the schedule, if you're only always computing parts of the schedule, not trying to redo it, then you have the faster computation of the schedule. And as I said, it's compositional. Let's go into a little more detail. So, as you saw in one of your CSP problem assignment, that was a exam scheduling, a room scheduling problem. So naturally, CSPs is one way to do scheduling. It's a natural way to think of scheduling. All right. So as we saw in a previous example, just to remind everybody, given you can think of a CSP as given this triple of the variables, a domain of values that you can assign to those variables, and the constraints. And the idea, as we remember in the CSP, is that you want to find a consistent assignment of the values to all the variables in V. Right? Everybody remembers that, I'm sure. So, as remember, these are also a reminder of the steps that we took before, with a little addition of this filtering, and I'll explain what that filtering means in the context of scheduling. So the idea is to propagate the constraints to establish the current set of possible values for the variable for each unassigned variable D. Before, if you think about that, you could think about it as every time you make an assignment, when you're doing your exam scheduling, it would reduce the number of rooms or different setups that you could do. And so that by propagating what values were now accessible in the next iteration, you've done your filtering. All right? If no unassigned variables and no inconsistent assignments for all variables, quit. Otherwise, select an unassigned variable D, select the value from V to assign to D, and go to step 1 until all of them are assigned. And this should all just be review for everybody, except for this one part about filtering, which is a new name for essentially doing that kind of forward checking or maintaining the, every time you make an assignment, what are the variables, what are the values that are now legal to assign to the variables. Okay. So there are two sort of methods in which to, general methods for doing scheduling. One of them is to assign fixed times to the tasks. And you assign start times to the tasks so it's consistent with assigning the resources to them. Another way of doing that is not to assign fixed times in order to enforce ordering, but just to put ordering constraints between tasks in order to make sure that there's no conflict. And we'll go through two different examples here. So one of the things about fixed times is when you do a fixed times, you can say, here's the start of an operation, here's the start of the next operation. But there's another model that you could do that still has assignment of times to it, but it doesn't limit it to a particular start time, a static start time. And that other one is called flexible times. All right? And what flexible time says, essentially, that you can start anywhere within an interval, and it will still be consistent within the overall everybody else executing. And so, for example, here, if you have this one is a flexible time, the flexible time might be from here to here, and that says that this can start anywhere, this can execute anywhere into this window, and that will still be legal for any time for this to execute, given that this is a precedent constraint and this must happen after this executes. So these windows here represent the flexible times for each one of these operations. And specifically what a flexible time represents is the earliest start time, the latest start time, the earliest finish time, and the latest finish time of that task. All right, so it gives you an interval, a window in there. And by doing that, you can maintain slack in your schedule and flexibility in your schedule, but still have ensure the consistency that you want. All right? Now, your question should be right now is, well, how do I come up with those flexible times? And how do I maintain them? What's the propagation engine that's going to give me that? So we'll talk about what that propagation is. In fact, it's going to be this. All right? So the role of these kind of filtering, as we saw in the CSP techniques, is to basically, every time you make an assignment, is to prune off all the inconsistent values that you're going to assign to the start times and the resources to those tasks. You prune them off so you don't end up searching those, and you only search the ones that are valid to look for. Obviously, the higher up you prune, the more you can prune off on the search space. Ways to maintain sort of these propagation engines that allow for this pruning. One of them is a temporal constraints, and that's using something called a temporal network, which I'll refer to. You also see in the literature as simple temporal problems, STP. I'll always refer to it as STN. So when I'm saying STN, I mean a simple temporal network. And resource constraints over here, which are based on these different dominant conditions. This is from Ursula from 1980. Edge finding is another way that you can limit which ways you want to do. And we'll look at each one of these things right now. So a simple temporal network is an edge-weighted graph of time points expressing constraints of the form that here's a time point on J and time point. The difference between the distance between this time point and this time point has to be equal to or greater than A and less than or equal to B. And what A and B there are, A is the lower bound and B is the upper bound, and the value between the weight on that edge has to be in between that to be consistent. Any value outside that range will not be consistent. Okay? The domain of each time point is a single interval, no disjunction. Basically, each time point means it can start at its lower bound or anywhere between its lower bound and its upper bound. All right? This encodes, you can, using this formulation and this graph, you can encode a broad range of constraints, as I said, domain independent constraints, temporal constraints these are. So some examples are finish to start. So as we said, a precedent constraint, and that means that the lower bound is 0 and the upper bound is infinity, right? So that means essentially at the end of the task, you can start anytime up to infinity out. Naturally, infinity is not a real value here and you have some horizon, but this is a 0 to infinity precedent constraint. A start to finish would mean that this would be the duration of a task. So you can imagine a task being represented by a start point and an end point. T1 is the start point, T2 is the end point, and the duration in there would be that link, the edge between that would be the duration. So in highly uncertain times where you don't know the duration, you can imagine that being something between, like, say, 10 and 15 where you have an uncertain duration. It's hard to reason about uncertain duration, and you'll see that. Typically, you'll see these things as being the upper bound and lower bound being exactly the same. Say the duration is, for this operation, is 15. And so you'll see both of these being 15. Start to start means that these cells, for example, would have to have a same start, and that's because if you have a lower bound and upper bound of 0, that means the distance between these two time points can't be any more than 0. So that means that these time points have to start at the same time. Okay? There are ways to compute the arc consistency and to ensure the consistency of the graph of the STN via an all-pair shortest path algorithm. Now, that should seem a little weird to you because if you're thinking about it, lower bounds and upper bounds, why would shortest pair work for both of those things? Why would, if you have a graph and you're trying to go through that graph and you have edges on them, why would shortest pairs, you can imagine it working for one of the bounds, that you can't go any farther. So if you think the most constraining upper bound, for example, if you had an upper bound of 25 and another upper bound of 20, the most constraining upper bound would be 20, and you'd have to finish by time 20, right? But if you're going the other way, the most constraining lower bound would be, if you had 15 and 20, the most constraining lower bound would be 20, because you'd have to start, if someone said, oh, you have to start by 15, oh, you have to start by 20, then to be consistent, you'd have to start by 20, right? So that seems like, the lower bound seems kind of like, that's the longest path, right? Not the shortest path. And the way they get around that, it's a little trick, is that they turn the edges for the lower bound into negative numbers. All right? So that negative 20 is shorter than negative 15 in my example. And so you end up doing shortest, all-pair shortest path, something, they used Dijkstra's and then Ford Washout, and now they have incremental models. They also have matrix models for doing the all-pair shortest path. But by doing that trick of putting the lower bound into a negative number, that's how you can get that shortest pair to apply to the lower bounds. Okay? All right, so here's an example of an STN. Here's our problem that we had in the beginning here, right? And here, let me just give you some examples, some pieces of this. I can already see I'm not going to probably get to the coordinator's example already, but we'll see. Here we have CZ. Every STN has to have an anchor point. You have to have some anchor point in the graph. And so this is typically defined as the CZ point. 0, 0 is often the point to it. It doesn't have to be 0, 0, but it has to be some constant value that's assigned to it. All right? And here are the time points that are represented for each one of the tasks. So let's going from the top here. We have a, remember we had a release date here. So this is representing the release date. It's saying none of these tasks can start any earlier than this release date. So this is going to be some value from 0 to whatever the release date is up to here. And that's the lower bound on that. The higher bound is the infinity, so you can go forever you want, because we didn't have that yet, any upper bound of that. So we'll go ahead and do this. And then we have these two time points that represent this task. All right? And the duration between these is simply this duration. And as I said, frequently they're always the same. So the yellow one represents the duration. The lower bound and the upper bound are the same, so it's a static number of that distance. So that's the duration for op1 and op1. Again, this is the precedent constraint. This operation has to start after this operation ends. So from this point on, you have 0 to infinity here on this edge here. So that means that this can go anytime, push downstream anytime amount at once, but it has to come here or later, based on this lower bound of 0 being the gap, the weight between this edge. All right, everybody understand that? Okay. So same thing here with the duration, as we said before there, another precedent constraint and a duration here. The interesting thing here is that this now is the deadline. Remember we had the due date constraint in that problem up here, this one right here. So the way that's represented is here is that you have a 0 down here, it could be infinity, but 0 representing the earliest possible time. And then you have the deadline constraint, which represents the upper bound here. And so what the STN propagation will do is guarantee that these things will stay in place. If you try to assert something like, ooh, this duration is too long for this deadline here, the STN propagator will spit out a violation and say, we're no longer consistent. And even better yet is that, depending on what algorithm you use, it'll spit back a cycle. basically you'll go back and you'll see as you're doing your all pairs, you come back, you end up getting a negative number coming back out of here. And that cycle will give you an indication about what constraint may be problematic for you. Usually when you're inserting a new one, you already know it's problematic. The new one's problematic. But you can also find other things about it, all right? And that helps you when you have to resolve issues. Because when you have uncertainty and you have new things happening, you'll often want to figure out what's the best way to repair it. And by locating the cycle, it helps you to kind of focus your attention on what you might do to repair it, whether it means removing a task or asserting new constraints or whatever it is. But it helps you identify what's wrong, all right? So anyhow, so these are some of the STN things. This is one for the other job that was done. Again, release date 2, the deadline date, the due date 2, and other tasks here, okay? So let's go through some quick examples of assigning new constraints in this STN. So we're scheduled op 1.2 at time T1. So it's T1, we're not saying T1 or later, we're not saying T1 earlier. So that way both the lower bound and the upper bound on this constraint has to be the same. Coming from C0 makes it an absolute number. This will have to start at time T1. Okay? So you can see it's a very natural way of expressing temporal constraints in the model. Another one is schedule op 2.1 before op 2.1 before op 1.2. Here again, we're just putting a precedent constraint between these links here, and this says that this has to go after. And notice, if we can assert this, that means that everything, that this is guaranteed this will happen after that. And here's the zero infinity constraint that you see with the precedent constraint. Okay, so that was an example of the STN. We use STNs a lot in our lab. STNs often been used frequently by NASA. They're used often for things where you have to do this continued scheduling and planning through execution of the plan and the schedule. Another way of doing it, as I said, was this kind of filtering that we showed in that CSP series of steps is this dominance relations of Oersler's dominance conditions. And basically what it's saying is this is going through the 4 possible conditions that you might have when you're considering the order of assigning 2 operations. Op I is before op J, op J is before op I, so it's either this way or this way. They can't overlap because they're using the same resource. That's inconsistent, or both options remain open. And by following these rules, you again can kind of prune out which steps you're going to do. You can look at 2 operations and say, oh, okay, I can do this one or this way, and I can start pruning out. As soon as I make a decision, I prune out the other ones. Okay, edge finding at a general level is this idea of determining what operations share temporal constraints when suddenly a resource is introduced. If all these resources, if all these operations are candidates to use the same resources, then you have a sequencing problem. You know, what way can I put those guys in on the resource such that I can accommodate all those tasks? And what edge finding allows you to do is essentially find constraints for the end times of these operations, such that if this guy, imagine this guy had a due date that was really early, but instead we scheduled it first here. We scheduled these guys first and pushed it out and didn't leave enough room for this guy. Then when we put this guy on here, the only way he could go, only space for him would be here, but he would be violating his due date. So by propagating those due dates and those constraints around it and establishing times for this, we know that we have to push this guy earlier, then find this guy, and then we can have the bin packing problem done, and we're able to sequence them such that they're all satisfied. So all that edge finding is doing is basically establishing the due dates for these things such that they won't be inconsistent given they're all using the same resource. Okay, so here is sort of the generic formulation of assigning a task, resource to a task. The idea here is you have this assignment activity, you have these resources, and you have this time things here, task 1 and task 2. You generate the resources that are applicable to that task, and then you look at all the possible intervals that might work for that assignment. All right, and by the intervals, I mean it's temporal intervals. So if you had a timeline in which there were already tasks on that timeline, then you'd have to look between each one of those tasks on the resource. We often refer to them as slots on the timeline. to see if these things can fit in there such that they can be serviced by the resource constraint in the and still accommodate and are consistent with all the constraints that might be specified on the tasks themselves, such as precedent constraints, such as deadlines and start times. So you go ahead and generate all those possible intervals that it can do, and from those intervals you may have some kind of a objective function that you want, or some kind of heuristic that you want for selecting the best one. All right. So you apply the filtering techniques to start the times, resource alternatives of the unscheduled activities, and then these were already on there, and from the slots you could have looked here, you could have looked here, maybe it might have fit here, given the constraints, and you pick that slot. And you can see what I mean by a slot, right? And by doing that, you've now kind of maximized the value of that schedule, whatever it is that you're trying to maximize on things. It's not optimal, it's usually heuristics, okay? But again, we're thinking of working in this context of continually solving the problem. So being optimal is not all it's cracked up to be if it takes you days to get there, right? Okay. So now we have this kind of core search procedure, whatever it is, based on this sort of simple model with variable ordering heuristics. We're picking which tasks we do, and then we're picking out which value we're going to assign to those variables. And then we're going to embed it in sort of a larger optimization problem, a frame structure for building larger optimization issues. So this should sound similar to you like local search. Remember where you have this idea of you have this constructive phase where you construct a solution, and then you might be able to find neighbors of that solution. So the constructive phase would be just generating the initial schedule here, and then you might have techniques for trying to pull things off and put things on to make a better schedule in terms of whatever your metric or your objective function is. And so that would be a larger scale optimization there. You can backtrack, you can dynamically change the variable ordering, iteratively re-invoking the core procedure, and we can use the solution generator to see the local search. All right, and we'll talk a few more about these things later on in the lecture. Okay. Some of the search heuristics that have been successful, Norm Sade and Chris Beck have talked about resource demand contention. The idea here is that you're trying to figure out which variables you want to do first, which assignments you want to do first, which tasks you want to solve first. And one of the ways that you might do that is look at the ones that you do sort of an abstract modeling of what you think are going to be the bottlenecks. All these guys use the same resources basically in the same time window. And you think, wow, that's going to be a hard one to solve because that's going to identify bottleneck resources. So you do some sort of loose reasoning about that, and then you go ahead and schedule those guys first because you realize that they're going to be the most constrained. All right? So Norm Sade and Chris Beck both did that a lot. FLAC and temporal flexibility. Here is this idea of choose a pair of activities with the least sequencing flexibility. Again, another notion of most constrained. So if you have a lot of flexibility in the schedule for tasks, and you assume that they're easier to place on later because there's more flexibility. But if you get them, as you get them tighter and tighter, you realize, I don't have much flexibility here, so I better try to put them on first, right? And so that other tasks don't rule them out. All right. And then minimal critical sets is this idea of putting things that use the most capacity on first. And resource envelopes is, again, another abstract modeling of where you have this kind of envelope of things that you've picked out based on the resource availability that's pushing down on when things can put, and you try to schedule it within those resource envelopes. We won't go into details on these two. Okay. So one of the models, as I said, is for when you're doing this kind of CSP type of modeling, is that you can do constraint postings. Rather than assigning individual start times for each task, you can insert precedent constraints between tasks in order to deconflict them, basically, so they don't overlap and on the same resources. So in this case, the variables are the orderings of the operations. So, and the values are wherever you put those precedent constraints, where before is a precedent constraint. So constraint posting and propagation in the underlying temporal constraint network, time points, and there are distances. So here's an example of how that works. Here you can imagine that this is a time feasible network. By time feasible network, it means it's fine, the times are all fine, but what is not fine is that we're oversubscribing the capacity of the resources. So suppose that the resources only allow for that much work to be done. All right? These are peaks, and they're above the capacity of the resources. So somehow you'd like to be able to solve that problem. You solved it in terms of its temporal constraints, but you haven't solved it in terms of its capacity constraints. So what do? So you take a look at these things, and then you start looking about resource leveling. You identify tasks that are contributing to that peak, their usage. And then you try to figure out an ordering that will allow you to switch them around. By switching that ordering around, you might be able to alleviate that peak. So for example here, we were able to sequence these task 1 and task 2, and that means that they didn't overlap. That means that the resource wasn't overbooked, and we were able to reduce that peak. And so this becomes that assignment. That's the deconfliction in order to reduce the capacity constraint. Okay. So as I said, we talked about scheduling search procedures, and we talked about constructive procedures, so the greedy, the backtracing, the linear distance scheduling. As we said, there's also this iterative repair and local search, which is commit early and often versus least commitment winnowing of solution set. We're going to show examples of both of this in just a little bit. And the emphasis is on the retraction heuristics as well as construction heuristics. If you take a local search method where you have a big schedule and then you have a bunch of things that you weren't able to get on the schedule, but you think that if I do a different ordering of this schedule, I might be able to get these new tasks on that schedule, then you have to decide, all right, which ones of these things can I take off that will make it most likely for these to get on, and then hopefully I'll be able to take the ones I took off and find different spots that will fit in. So you have that selection problem. And so there's now not only the concentration about which ones we put on, but also the ones that we take off. Okay, so we'll show these examples later on when we talk about oversubscribed problems. All right, now let's talk about managing the schedule change. So this is what happens when uncertainty happens. We have a schedule, and now something's going to go wrong. How do we handle that? All right, so we design and use scheduling policies, different ways to handle it. Here's the proactive one. Generate schedules that anticipate uncertainty. Now this should sound a little bit like the planning strategies that we had, right? We had conformant planning, contingent planning. Remember, with conformant planning, we would try to adjust the environment such that nothing could go wrong. You know, if we needed 2 chairs to be red, we didn't say, oh, what are be the same color. We just painted them both red, right? That was kind of conformant planning. Contingent plans would be like, well, if it's red, if that's red and that's white, I'll paint one red. Okay. If something goes wrong, I'll do the contingency. So that's a kind of a proactive. We build that in advance into the schedule. The reactive one is, you know, something went wrong. All hell went wrong. Now I have to figure out methods to react to that and to adjust to it. Okay. Ideally, you'd like to be able to do both of these things, I think, in the real world. Sometimes your environments don't always promote this because often when you do this, you're giving up some optimality or some kind of efficiency in your schedule because you're making decoupling decisions here, so it can be less optimal here. Here, no matter how good you are at predicting there in advance, it's rare that you can actually figure out everything that you want to do here. And you don't know what the world's going to throw your way. And so you often need these kind of reactive methods to deal with the fact that something's going to mess up. All right, so approaches to managing changes. We want to build schedules that retain the flexibility, produce schedules that promote localized recovery, supermodels Ginsburg. This is that proactive model we saw on that previous slide. This is the idea of building basically points that if things fail, we have backups for them. Redundancies, different paths that can be taken. Incremental scheduling or a natural continuity as an objective criteria. One of the ideas here is to keep our schedule. If we have an incremental schedule, then doing reactive repair on those incremental schedules is a good thing. If you're maintaining, like we saw with flexible schedule time frames, then if we say, oh, if something finished later than we anticipated, it's okay as long as the slack hasn't been violated. But if we get a violation in a propagation engine, then we have to react. So that incremental technique allows us to keep adding that and maintain some stability in our solution. Okay. So let's talk about incremental schedule repair. There are several competing approaches to maintaining continuity in schedule repair. One is to be a minimally disruptive schedule revision. As I said earlier in the lecture, you want minimally disruptive in particular in the case when you have humans as people that are executing the schedule. They're not very good when things change all the time. All right? Priority-based change, this is where you only change the ones that are of, you change the lowest priorities first so that they're not as important. And regeneration preference for the same decisions. If you regenerate the whole problem, resolve the whole problem, rather than doing an incremental change, then you'd like to have a tendency to go back to the same decisions you made, as long as it doesn't get in the way of solving whatever caused you to reschedule. All right. So it's sort of weighting yourself to go back. If I use resource 1 and resource 2 to solve this and this particular ordering, then I have a tendency to go back to that if that's not going to help me solve my problem. All right. The critical issue here is how to trade solution stability concerns off reoptimization needs and computational costs. As I said before, you can, if you have something go wrong, you could always think, all right, I'm going to take the current state, wherever I am in the executing schedule, and just resolve the problem. Just resolve the problem, given that current state. But if I resolve the problem, that means I could have vastly different orderings, vastly different resource assignments. And it could be cognitively very disruptive. Now, if you have all automated effectors, essentially, who aren't going to be disrupted by that, then it's not a real problem, right? They don't care. It's not going to bother. But for humans, that would be that is problematic. The other issue is that resolving the whole plan can be computationally very expensive. And if you can't keep up with the pace of change in whatever environment you're in, then that's not going to be successful either. Okay, so what are some of the ways of hedging against uncertainty? Temporal, as we showed with the temporal networks with the flexible time bounds, you can hedge against some of the uncertainty of that, because even if things complete late or start late, as long as they're within the slack times that are represented by those flexible times, then you're okay. You know, it's only when they violate that thing. So you're already hedging against the uncertainty about when things will actually complete or start. So that there's some hedging that occurs there. There is this notion of strong controllability and dynamic controllability. These things are both notions of that if you have a strong controllability graph, it's like conformant planning in the sense that if something goes wrong, you're guaranteed that it will still work, but you often are giving up, as I said, optimality or efficiency of the schedule in order to make those guarantees. Okay. Contingent schedules, notions of disjunctive temporal networks, meaning that you know it could be this long, or it could be this long, or it could be this long, and so you have multiple. One way to think of that is that you have multiple disjunctive networks that either one of them, any one of those networks may be in place, but you can imagine that as you have different changes in different places on different disjunctions, then it would require a huge number of disjunctive networks to represent all the possible things that might go wrong. So managing those combinatorics has not been done very successful up to this date. All right, it's a natural representation for it, but the combinatorics are overwhelming. Also, you could do something where you project likely failure points and generate explicit contingencies. Or, for example, is if you have some information about the model that tells you how likely it is that the outcome of a task is going to fail, or that it's going to extend beyond the duration of a deadline, which could be considered a failure also, that you will say, well, gee, I need to put redundancy in there. I'm going to have some other methods do something else in order to make sure that that gets achieved. So do it two different ways. So if you can identify that, usually through some kind of probability analysis, like we saw in our Bayesian reasoning, that you can identify certain things that may be weak in the schedule, then you can go ahead and try to put in some redundancy in order to ensure that that will get done. All right? So let's go, we're going back to the original question about how does planning and scheduling work together. So here we have a planning, we have a set of goals, and then the sequence of goals and construct a goal achieving action sequences. So we figure out these set of actions that will achieve those goals, right? That's just like what we saw in planning. That's what planning returned. Okay, now what scheduling is going to do is now we're going to actually allocate the resources to these tasks in order that they get done. Here we didn't really consider resources, and now we're actually allocating those resources. And that's been the kind of traditional conventional distinction between scheduling and planning. But as I said, it has blurred over time. Okay, so one of the things to think of a problem, as I said earlier, is that it's a resource-driven problem. A problem where the assignment to what action to do is very, very dependent upon what resources are going to be used and what are available. So it becomes something you want to think about first. So the principal form of the goal interaction is the competition for the resources. So upfront planning process is separable and limited to achievement of individual goals. At its core, these are essentially scheduling problems. If you don't consider the resources, then these problems, you're going to be defeated by these problems if you only think about it in terms of planning. All right? But the allocation of the resources introduces planning subproblems, and I'll show you that. So here's against, we have a resource-driven problems, and we construct goal-achieving sequences, right? And allocate resources and assign times. So here what we have, the issue here is that this is really the dominating, they're competing with each other. So these will help you determine which goals are going to be done and in what order. All right, so where's the planning in a scheduling problem? So we've talked about where scheduling is important to the planning. Now where is planning important to scheduling? So if you're thinking about managing shared resources and each resource has a setup, some kind of setup. As I said earlier, you have to set up a machine to do a particular configuration in order to accomplish that task. That would be a setup. If you have to go, if you have situated tasks such that task A is in one location and task B is in another location, and you have to figure out where, in order to do task B, you have to be at that location, then depending on what resource you're on, you have to figure out different travel times to get there. And so if you think of that travel time as a setup in order to achieve the necessary precondition of being at that location in order to execute that task, depending on which timeline you put it on, that setup task is going to take a different set of time. It could be if you're very nearby, great. And depending on what slot you pick on those things, the time's going to be different. So here you're actually trying to decide what actions you're going to take in order that you can then do the assignment for the resource. So here we have our core procedure for generating the options. And now, with this additional thing of setups, we have to consider. We're looking at the slots here, right? Remember how we were picking the slots before on the timeline? Well, here is one. Here's the action that was before on the timeline. Now on this slot, we have to concern ourselves with this setup time. Here we might have another setup, and it might be a different setup time. And so in order, we have to actually plan these actions that have to get done, right? What's typically done differently in scheduling than in planning is planning has this very kind of general model of except for the HTNs that we saw towards the end, where we have operators and we have objects, and we try to put them together based on some kind of chaining, right? Or different graph plan, or partial order planning, or all those techniques. Here, these things are more engineered in the sense that they say, oh, I know what I have to do here. I have to do some kind of travel. And so I'm going to reason about traveling. So in this way, it's less general than planning. But you still have to decide about what steps you're going to do here. All right? So for example, if you're doing travel here, you might have some, again, floored washout, shortest path between all those things. And you might say, I want to minimize distance. So if both of these are both good, and my objective function is to minimize the make span of the schedule, then I'd like to minimize the time it takes to do that setup. And so I might pick the slot that has the minimum slot, minimum time. Okay? Okay. All right. So I'm just going to really quickly go through this. Here's an example of some setups here. This is for the Hubble telescope. You guys have all heard of the Hubble telescope. One of the things that when you're scheduling tasks for that Hubble telescope, scientists submit a bunch of requests, and as they submit those requests, the telescope, they try to plan out when those requests can be done. And one of the things about it is it depends on where the telescope is facing, to whether it can satisfy those requests, whether certain aspects of it are in a particular position, and you can imagine that all being a setup cost in order to do that. And so, for example, they have the changeover, the slewing, the setup time, and you have to figure out all that in order to figure out what can be to satisfy a particular request. So if you want to put this request here, you have to figure out what the times are in order for this to accomplish. All right? The way they did it is they took this abstract problem. They thought of the telescope as a single resource, and they have set commitments to it. And then now you're trying to consider, here's all the possible tasks that might go into this slot. And you have to figure out in this kind of setup, and what goes into the setup is this more detailed state here, where they figured out all the different pieces in order to figure out how much time and setup would have to be done in order to accomplish any one of these things. And I think most of the time they minimize the time, and they would pick the one that would minimize the time for the setups. All right? So what's missing? The scheduling models gain their power by making restrictive modeling assumptions. That's what I was talking about. They sort of say, we're just going to concern ourselves with temporal constraints, with some capacity constraints, and particular kind of setups, like, oh, this is travel, or this is slew, and this is kind of machine configurations. It's not doing general planning in this case. One way you might be able to get around this is, instead of being so specific, is use sort of a goal-directed, just as though we had done in planning, and be able to integrate the scheduling and planning together. At a larger level, you'd like to be able to do planning and scheduling in this kind of serendipitous mode, and where they work together and they work synergistically together. The challenge is how to effectively embed a planner within the scheduler to do that search process, or to embed the scheduler within the planner. There have been many techniques, attempts to do this, but none have been very successful. Most of them are still at a course level where we sort of plan, we schedule, we plan a little bit more, then we schedule. Course steps, not this tightly integrated way of doing it yet. Like I said, there have been lots of techniques attempted, but none of them have been terribly successful at doing that. Okay. Solving oversubscribed problems. So an oversubscribed problem is basically, I got more things to do than I can do. All right? I have resources, and I have these task networks that tell me the jobs I have to do, and I got more of them than I know what to do. So what do I want to do there? Then somehow I want to do something that will maximize something. Maximize the utility I get from doing whatever I do. Maximize the utility I do. Maximize just the number of tasks that I do. Some objective function for what I want to do. And here, what's interesting about this is suddenly now we're in the back end scheduling is doing that kind of planning case where it's going to choose which tasks to do, right? Before it just tried to do all tasks. Now it's got to choose which ones are going to best maximize that objective function. All right. So I said some examples of objectives to maximize the number of tasks performed, maximize resource utilization. So what are some of the ways that we can deal with these oversubscribed problems? So here are some examples of them. Rover task planning, when members Spear and Opportunity, when they're out there and they're careening around Mars, there's a whole problem about what do you look at next? Where do I go to explore? And so they try to be opportunistic about that, but there are more people putting requests than they know what to do. And so they're trying to optimize. They realize they can't satisfy all scientists' requests. They're trying to maximize what they see plus what the scientists' requests are in order to achieve both of them, but it's oversubscribed. The satellite observation scheduling, Barbalescu et al., they have to schedule the ground stations for the satellites. There's a communication stations on all the grounds, and there's only so much bandwidth and so much ways of using it. And so they had to, you can't satisfy all of them. So again, this was a oversubscribed problem. Military aircraft, again, more requests than you know what to do with, and so you have to solve this. And this personal task management, which is a way of doing like meeting scheduling. So let's look at a couple of these. As I said, the approaches to the oversubscribed problem is this emphasis on resource limitations other than fuel orientation. That was David Smith. Formulation of partial satisfaction problems. Specify preferences over goals and combine with other preferences. We'll go through these. These are just general approaches, but here are some examples here. The idea here is that you have, as I said, too many things to do, and you have more complex settings that decompose into these kind of higher HTN fashions into lower level activity sequences or disjunctions, and you're trying to make a decision about which ones you should do. So let's see if we can get to this. So here are the two kind of general techniques that are used. One is where you explore, I don't know why this thing keeps doing that. One of them is you explore permutation space, and what the permutation space means basically is you pick an ordering of the tasks and you try to solve the task in that order. All right? And then you go ahead and you go and quickly generate a schedule. Do an evaluation of that schedule, get some, based on the objective function, get some value. And then you perturb that ordering of those initial tasks to some other ordering based on some property, and we'll talk about that when we get to squeaky wheel. And when you perturb those things to a different order, then you will try another option. And you keep trying these up to some set of either requirements of what value you want to reach or just some limit of iterations that you try this on. and you basically keep the highest one. And this is a way of sort of stochastically sampling the different search space out there until you get the highest values. All right, and that's working in permutation space. In the schedule space, this idea here is more like a local search. And here what you do is you go ahead and generate, using your constructive means to generate a general schedule. And then you look at the problems that you were not able to insert on the schedule. And then you think about ways to retract from that in order that you can insert the ones that you weren't able to put on. And hopefully you'll be able to put on the ones you took off, more on than you took off, basically. And so that you improve the quality of the schedule. All right? So here's one of the domains. This was done in the military domain for doing missions, for carrying cargo. You have this idea of flying out from the base, picking up some cargo, and flying back. You can also merge missions together such that you can fly out, pick up some cargo, pick up some more cargo, and then fly back to where you drop it off at the destination, and then come back to base. And frequently, these are oversubscribed problems, and your decision is you're trying to decide what wing should do each of those tasks. You know, depending on where the wings are located, they can be located at different places. They have different capacity airplanes, so some wings may be better to do than others. And you do that, you schedule a bunch, and frequently you'll have a bunch of tasks that you weren't able to schedule because it's an oversubscribed problem. All right? So the goal is to control schedule revision to accommodate additional tasks without relaxing constraints. You're trying to figure out some way to insert the ones that you couldn't get on, but you have to change the schedule because they didn't get on in the first place. So you have to change the schedule. So we're going to do some kind of retraction. And we're going to do this retraction based on what we call the footprint of the unassignable task. And basically that means if you look at the time of when that schedule, when those tasks might be able to go, and you look at the task underneath it, and each of those tasks underneath it, you think, all right, if I take some portion of those tasks underneath it, meaning that are simultaneous with that, then I might make room for it to be put on. And then I can choose from those tasks that I can take off based on different heuristics, based on thinking how easy it will be to return them back onto the schedule some other place. All right? If all the tasks are displaced to accommodate T, cannot be feasibly reinserted, and then you undo that. This is just basically you're iterating through until you can see if you can insert more than you've taken off and increase the value of the schedule. So here's an example. So here's an example of, here's all these tasks. They're all scheduled on the resource, on that wing, and this guy's the, well, I wasn't able to put him on initially in the constructed place. So now I look at the footprint of this guy, and sure enough, here are the problematic pieces over here. They're stacked up in the capacities. So I think any one of these tasks that are part of this footprint are candidates for retracting in order to get this guy on. So now I'm going to decide which one based on the heuristics, some heuristics. And I will go ahead and take some of them off. And I say I'm going to take T2 off. Okay, so T2 is up there. I'm going to take T2 off based on my heuristics. I pull that off. And now I'm able to insert T1. But now T2 is off, right? But lo and behold, I can go ahead and put T2 on here. So that's a favorable result. And so if you did that with every reconfiguration of every order in every place, you're back into the exponential space and time model that you don't want to get into, and you can't do that. So this is a controlled way. You only try it once. If you've already inserted this task on once, you won't allow it to be taken off again in subsequent versions, subsequent tasks. So it's a very controlled measure of way of sampling this kind of other ordering space in order to see if you can improve your schedule quality. So some retraction heuristics here are max flexibility. You take off the ones that have the biggest windows because they have a lot of slack in their windows and they're a short duration. You think, well, they'll be the easiest ones to put back on, heuristically, right? Another one is count the intervals that are at capacity, which the conflict with the task feasible window. Basically, pick the ones that have the least conflicts with other tasks, and then try to take them off first. And then there's this kind of slight rendition of the min conflicts, which is take the conflict count plus the duration of the actual task. All right? And these are just heuristics for, again, deciding which ones to take off. So sort of the general task swap procedure is to, given an unassignable task T, to insert into the schedule, identify where the conflicts of that task exist, retract one or more tasks in the conflict areas to free up capacity based on some heuristic values as you evaluate which task. Schedule a task T and mark it as seen. Reschedule the retracted tasks. If all retracted tasks cannot be rescheduled, recurse on them most constrained first. Okay. If all tasks have been tested, seen, and some remain unassigned, backtrack to original state. All right. So again, this is just a way to see if you can improve the schedule quality. This generalized task swap was tried on a different domain, which was the what's called the pickup and delivery problems, or dollar ride problems. Again, it's just going out, picking up, and delivery of cargo. In this case, it was people. And there was a benchmark, and this actually was able to. This benchmark was based on optimal means of doing highly constrained CSPs and branch and bound techniques, which take a very long time, short times on solvable ones, infinite time on ones that are not solvable. And this was able to match the performance of that with a much slower computational time. Okay. All right. So an experiment was, how does a schedule-based search procedure perform relative to a permutation-based search procedure in a given domain? So we talked about the schedule-based one, but we didn't talk about a permutation one. The permutation one that we used was the squeaky wheel technique, which was done, which is a kind of a famous idea, and it's a really simple idea. The idea is to give some kind of objective function to tasks that don't get on in the initial schedule. You just do some kind of permutation of the tasks, try to schedule them all. Some of them don't get on, or they do get on, but they're past their deadlines, and they're considered squeaky, right? Because they're problematic. And so they get the grease. And getting the grease in this case means you push them up in the order and you reschedule again. So they get the first assignments. And so you always give, and you try this, n number of iterations, and you try to keep the highest value schedule that you get replaced it. Typically what you need, of course, for this is, because you got to try so many different iterations, is you want a very fast construction stage. You don't want something that takes a long time to construct, because you're going to do lots of different renditions of it. So the idea here, is, as I said, is to generate a schedule with a schedule builder based on task ordering. If all the tasks are assigned, great. If an iteration limit has been reached, that's what I'm saying for the number of squeaky wheels, then go ahead and stop. Then reapply the task permutation resulting in the most assigned tasks and stop otherwise. Analyze the schedule. Here's where you're figuring out which ones are to identify the unassigned tasks, the squeaky wheels. Give some move operator and advance the squeaky wheels task a distance forward in the task ordering, and then repeat them again. Okay. So here's a really quick idea. It's limited here. We have this initial task ordering, T7, T5, T1, T2, T4, T3, T6. Build a schedule. We get all we could get. We weren't able to get T1, T4, T3. All right, so they're the squeaky wheel ones. So the new task permutation after moving the squeaky wheel forward is we moved up T1, T7, T4, T3. We moved up T1, T4, T3 up earlier. So they're going to get the resources first when we now try to regenerate the schedule for it. And we build a schedule with, again, now we have T4 and T5 not assigned, which is better than it was before, right? And we go ahead and we move it forward. We move T4 and T5. We build a schedule, and T1 is not assigned. We do a new task permutation again, move T1 up, and we build a schedule, and then all the tasks are assigned successfully in. Again, that's like, Shangri-La. We're in the perfect place here. That doesn't always happen that you get them all on. But by reordering these things, we're trying to get, again, sample that space that we can try to improve our schedule quality. Oh, okay. So just really quickly here, one of the things that was kind of interesting about that is we did this comparison between task swap and squeaky wheel. And what happened is that on the one domain, this Air Force domain, the squeaky wheel did better than the task swap. Okay, it did better all the time. But on this other domain that we did, which had priorities in it, task swap did better as you got more oversubscribed. In the beginning, they were basically the same, but as the problems became more oversubscribed, task swap did better than squeaky wheel. Okay, and so it turned out that this kind of priority constraint that you have to do, if you have to do all of 5 before you do priority 4, before you do priority 3, if you have that in your problem, then task swap was a better way to go. But otherwise, squeaky wheel was the better way to go. So it was just in this particular domain, but it was an interesting idea that it shows you that these weren't determinant factors, these features of the problem, but this was the determinant feature of the problem, that determined which approach worked better. Okay, So this just says basically that SW dominates in domains with no priority, regardless of other factors. But if you have to use priorities in which you have high oversubscription, then task swap is better. Okay? So we'll go quickly through this, I hope, and that'll be it. What is distributed planning and scheduling? A planning and scheduling process that involves more than one player, coordinated goal achievement. Agents have to work together in order to achieve a tasks or process or jobs. Coordinated action selection. You have to decide what actions to do. Should you do it? Should I do it? We may not have some centralized, deity that's saying you will do this and you will do that. You guys are coordinating. You're working as a team, working together. And the coordinated task resource allocation over time. So why distribute the planning and scheduling process? Why would that happen? Well, you can imagine organizationally, things are just distributed. People don't have visibility to other people's processes, right? You can also imagine computationally, it might be faster in terms of the organizations. So many applications are just inherently distributed. There can also be performance advantages to distribution. So some examples of doing this are you can have, like I said, you can have many scheduling problems. You can have competing objectives. Some agents, you have self-interested agents, and that means that they don't really want to coordinate, but they do want to maximize their own priority. So if they maximize their own utility, they have to work with you begrudgingly, right? So there's ways of working with that. Controls are already distributed, communication constraints, computation constraints, and dynamics. These are all things that you have to consider in these kind of environments. So I'm not going to go into too much about self-scheduling, but this is sort of like if you think of that, like the swarm mentality, this idea of lots of little agents making lots of decisions in order to get an emergent behavior. All right, and you can imagine them working together to get something done by making lots of local decisions, but you usually have no global view, and often you don't have very good global efficiency in the schedules. But these are highly dynamic. They are very robust in the sense that if one thing fails, another little local agent is going to pick up and take the place of that. So they're very, very robust against failures. And then you have this kind of management of advanced schedules where you have really highly coordinated activities, but these things can be more brittle because they require lots of sharing of information. And if one guy doesn't do it, you have to try to figure out how to bring in place of those. All right. So some of the mechanisms that they use for trying to do this distributed scheduling is the kind of market mechanisms, distributed constraint optimization problems, and then heuristic scheduling. All of which are complicated by the fact that nobody has a global view of the problem. And so they have to share information, and there's latencies in that information when they arrive, and you have to make these decisions. Okay. So as I said, just really briefly about self-scheduling. As I said, they're very robust. They have this emergent global behavior, but because every local guy is making a small decision about who's going to do what, about it's going to do it, it takes you don't have like a global perspective on it, so often it's not very efficient. But if you have 1,000 agents that can do it, and you have a ton of resources, you don't care about the efficiency of the schedule. All right, let me just go on here. Okay, so market mechanisms. Market mechanisms are based off, the original market mechanism was this thought of an auction. And there was a thing called a contract net protocol by Reed Smith in the early 80s, which is essentially that says, I'm going to do an announcement. You guys are all going to tell me what you can do, given some tasks I set out there, and then it's going to come back here, and I'm going to make a decision about it, and then I'm going to send those assignments back out to you, say which ones of you are actually going to do the work on it. All right? So one of the quick ones was the Morley's GM paint problem. Here was the bid parameters with the same color last track, space, announcements, and this guy, you have a rule for making decisions based on the bids that come in. And you choose which one. This guy makes it. Okay? So the advantage is that there's a complexity reduction. There's a lot of robustness in this. Again, if suddenly I'm doing a task and I think I'm going to do it, and suddenly Rushan drops out of there and she can't do it anymore, then I'm going to say, all right, anybody else in the bid who said they can do it? They said yes. Then you can go ahead and step in there, and so you have this kind of robustness in the schedule execution. All right. This is just another example. This is for radios, monitoring frequencies. And here again, we send out an announcement. The radios all generate bids that they can cover these certain frequencies on the radios. And then it says, OK, I'll figure out which one to do, and I'll send it back to the manager. This guy will make a decision, and he goes in and says which one of those nodes should go ahead and monitor those frequencies. All right. This is again another example of that. This was within deciding what the rovers should do. I'm not going to go into great detail again. Again, it's the same kind of announcement, bid, analyze the bids on the auction side, and then send out the assignments. All right? So, right. Okay. So let me just kind of step back because we're about to run out of time here. We may pick up a little bit later. I'll see what happens after knocking. Actually, it's Wednesday. I won't be here, so I won't be picking it up. So the general what I wanted to say is that I gave you a breadth-wise, obviously now depth-wise, introduction to lots of different techniques that are used throughout this kind of scheduling world. And I showed you how the scheduling is pushing you into planning, and planning has to deal with some of the problems that have been traditionally thought to be scheduling, which are resource-constrained kind of problems. And so there's an open research agenda about really how to get those to work in a tightly coupled way and not in a coarse coupled way. In addition to it, what I was showing you is that what's important often for all these systems, in particular in scheduling, is that you're not just solving a static problem. You're solving a problem over execution. As resources fail, as execution times take longer, or times are shorter than that. And so you need these techniques that can be incremental, that can build off these solutions, and so that you don't have to resolve the whole problem. One, because of computational reasons, and also two, because it's not efficient in terms of the human beings who might be part of those processes. It's too cognitive disruptive to them. All right? So we have these techniques. We have the different styles of doing this. It's playing off of the techniques that we learned earlier in the course, the search, the local search, the CSPs. It's playing off these things, but giving real values and formulations to those pieces in the scheduling piece. It's one of the things, I'll end with this thing. One of my colleague who's been working in this field for a long time is probably one of the seminal figures in scheduling. His name is Steve Smith. Was asked once a question. It's like, isn't that a solved problem? Isn't scheduling a solved problem? And he started to think about all these things that we talked about here. And he remember his big thing was that it's just beginning. It's not a solved problem. Even though you think that everything's been done, and think that you have all these mathematical operations, as soon as you put it in the real world, many of those techniques fail to keep pace with the change of the world. So I'll stop with that right now, because we are at 2:51. And I'm over my deadline, so my utility has gone down. And we'll see. I think Vico will pick up on robot. Is it path planning next time? Yeah, I think he's doing path planning on next time. Okay, great. And don't forget, if you haven't done it already, start to think about your progress.